is dipping geometric shapes in a thermal fluid to see what different bubbles come up. And it just so happens that right up the road, Professor Tromba is a world expert on this stuff. And so he's graciously agreed to give us a little talk on the mathematics behind minimal surfaces. So a little bit about Dr. Tromba. He received his bachelor's from Cornell and his PhD from Princeton under the direction of Smale. And Smale actually received the Fields Medal at the time that Professor Tromba was working with him. So that's sort of the mathematical equivalent of the Nobel Prize, really high-level mathematicians. He taught at Stanford, at the Ludwig Maximilian University in Munich. He's been a visiting professor on 4 different continents. He's been a director at the Mathematical Sciences Research Institute. And last but not least, he's a distinguished professor of mathematics at UCSC. And throughout his career, he's been writing books pretty much the whole time, as far as I can tell.
Yeah.
And so if you go on to take vector calculus for a year, you'll probably use his text, Vector Calc, which has been in print for about, 40 years?
Almost 37, 38 years now.
So 37, 38 years. So it's a very widely adopted text. In addition to that, he's got a collection of research-level texts that he's written with very prestigious co-authors as well. So this collection of texts here, it's all on today's talk. So why don't you take it away and tell us.
Thank you very much, Brian. It's a pleasure to be here. Yeah, so the mathematical theory of soap bubbles, soap films. This is a soap bubble. As I said, I was jumped by security guards in the Zurich airport when I tried to board a plane with my gun. And they wouldn't believe that this was a harmless, but what can you do? So everybody knows what soap bubbles are. Soap bubbles are an old pastime. Even there are pictures of soap bubble blowing children on Etruscan vases going back thousands of years. So here's the soap film, and you just take a wire, and it turns out every time you dip it in, you get a beautiful soap film. And they all can take many, many different shapes depending on the wire. And one of the unsolved problems in the area of minimal surfaces, still unsolved, is whether there's a finite number of possible soap films that you can find when you pull out the wire. So you can have arbitrarily large number of solutions, but we don't know whether you're actually finite. And you can always find a wire. Let's say given n, you can find a wire with n solutions, but it's not known whether it's finite or not. And that's one of my areas of research that one of the theorems I worked on, and proved that if there is such a wire, the chances of finding it is 0. So it's some kind of probabilistic result. But I've actually been involved in writing 4 theoretical volumes on the subject. I didn't bring my first volume here. This is about 1,500 pages, so there's a lot of mathematical theory, most of it very, very difficult. And this is not a math seminar. This is, I think, a popular talk. So I'm always happy to answer questions about the theory of minimal surfaces. But as just even to try to give a mathematical talk, couldn't usually get out of control and lose a lot of people. So I remember once when I was young, I was getting on an airplane, and sometimes you sit next to people who never want to talk to you, and other people start asking you questions, and they ask you what you do for a living. They say, I'm a mathematician, and the first response is they start telling you about their terrible experiences of mathematics, what a horrible teacher they had. So I feel like a Catholic priest hearing a confession. And then some people feel that they know something about mathematics, and they ask me, well, what's your field? So rather than saying the calculus of variations or partial differential equations or Riemann surfaces, which is really my field, I said I'm into soap film and soap bubbles. Oh, and some people get insulted because they feel that I'm being patronizing. That obviously nobody, no university professor could be involved in soap bubbles or soap films. So I decided to write a book for general population. Actually, it was the first math book in the Scientific American Library series. And then later we expanded with my colleague in Bonn, Germany, called The Parsimonious Universe, on shape and form of the natural world. So this is a popular book to try to explain why this is interesting. Now, it's often the case that it takes a very, very smart person, a genius like Leonardo da Vinci or Einstein or other people, to see that there is great significance in the seemingly insignificant, that the trivial can be actually rather profound. So, in fact, for most of my life, I've been driving around California with my license plate. I'll tell you my license plate. It says Max Min. And I remember right after 9/11, I have a very old uncle. He was in his 90s now, but he was in his 80s coming to visit me. And I went to San Jose Airport to pick him up. And the whole place was mobbed with state troopers and police and paramilitary. And I had to wait in a huge line to get in the parking garage. And finally, one of the troopers came and flashed a light in my car, and it goes like this. He asked me to roll the window down, so I'm rolling the window. Then this vicious German shepherd looking at me, and I think he's going to leap through the window in any second, go for my throat. And he looks at my license plate, shines a flashlight on the license plate, looks at me and says, "You teach calculus." So I said, "That's great. That's a university-educated state trooper. That's wonderful." Okay, so here's one of my favorite quotes. It goes back to the 13th century, to the man who wrote the Inferno, Dante. "All that is superfluous displeases God in nature. All that displeases God in nature is evil." Okay, so I want to actually, I'm going to kill myself with my shoes here. They have to improve laces, actually. I think they have. But anyway, so I'm going to provide some context because the thing that I've learned about most math lectures and math classes is you go in, and if you're in high school, you're in algebra, and you want to know, why am I sitting in this algebra class? Why do I need to find the solution of a quadratic equation? You never get to the cubic equation, except if you take my history of math class at UCSC. But anyway, why am I here? Why am I learning all these things? It's so dry, it's so boring, it's so uninteresting. And even if you look at university students that sit in calculus class, let's say UCSC or wherever I taught, they actually don't know why they're actually sitting there, other than it's a requirement, and they can't go on in their studies unless they do it. So that makes me actually quite sad, because I'm a mathematician, and mathematics is probably the greatest achievement of mankind, in my opinion. Okay, so I'm going to give some context before we go on. Before I do that, I'm going to tell you that the reason why soap films form, this is a soap film, is because if you put it in water, why do you need soap? Because the soap actually reduces surface tension. Surface tension is very important. And that's why when you reduce surface tension, you're allowed, nature allows the film to form. So you can form many complicated types of films. Both of these, the soap bubble is actually a surface of minimal area. Nature is tending to be very economical. You blow some air in, and then the surface that forms, because you try to reduce the total energy of the surface, which in this case is proportional to area. A ball, a sphere, is a surface of least area containing a fixed volume of air, whatever that volume is to flow into. So to actually prove that fact mathematically is extremely difficult. And a minimal surface, a surface here that forms along the contour, there's no air involved. This is, again, a surface of least area. So now you can actually formulate the problem mathematically. For those of you who had multivariable calculus, there's it's an equation of this is a disc-like surface. Surfaces come in all kinds of shapes and forms and topological types. I'll mention that later. But they're all surfaces of least area. Some containing a volume of air and others not. Okay, so why should anybody be interested in them? Well, again, there's the old saying that, you know, a genius can see the significance in the insignificant. So let's go back before the rise of Greek civilization. For thousands and thousands of years, even going back for as long as we can even have any information about the world, it was a very, very frightening place. There were tsunamis, there were earthquakes, there were horrific volcanoes, like that in Vesuvius in 79 AD that wiped out Herculaneum and the city of Pompeii. Devastating events, and people didn't know why these events were taking place. And so in some areas of the world, well, in most places they thought it was the work of the gods, so-called gods, and in some places in the world they even had human sacrifice to appease the gods so that there wouldn't be any droughts, there wouldn't be any, you know, hurricanes, tornadoes, or whatever, earthquakes, whatever you name it. And so for all of these people, the world was terrified. Then suddenly there was a civilization, Greek civilization, about 600 BC, that said that the world is not terrifying. The world is rational. The world can be understood. This was so unbelievably different from anybody that came before them. But they went even further. Let me go here, and you can see here, this is one of the things I didn't mention, the solar eclipse that really scared the devil out of people. He is one of the first mathematicians. Pythagoras, everybody knows his famous theorem. Pythagoras was a philosopher who was born on the island of Samos in the Aegean, and he established a school in southern Italy, and he taught that the whole world was designed mathematically. And this was followed up by another philosopher, Plato, who said that not only is the world designed mathematically, but that's the only way to understand the natural world. That the language of mathematics is the only language which will enable mankind to understand the natural world. And here's a mosaic of going back thousands of years of us depicting Plato in school in the ancient city of Athens. Now, the word mathematics actually comes from the Greek word mathma, means recognition, cognition, understanding, which is strongly suggestive of the fact that mathematics was created in an attempt to create a special language in which we can understand the world around us. So if we go back to the ancient Greeks, the Greeks looked around them and they were fascinated, they were curious, they were interested in having that sort of mindset that they could understand the world, A, and B, that they could understand the world through mathematics, forced them to start asking lots of questions about the world. For example, they wondered about the shape of things. They looked at the moon and they wondered, why is the moon round? They certainly knew that the earth was round. And even had an estimate for its circumference. Why are the planets round? They looked at crystalline shapes and they wondered why crystals were shaped the way they were. And that may have led them to classify the 5 known regular polyhedra. That you can see the icosahedron, dodecahedron, tetrahedron, and octahedron. These are polyhedra where each side is congruent to every other side. So they're identical. Now, not only did the Greeks say that nature could be understood and that nature could be explained through mathematics, they did something else which for me is very phenomenal. They really predicted the advent of modern theoretical science by saying nature follows laws, just like there are laws in governments, and that these laws are not ordinary laws, they're mathematical laws. So that was a stunning insight into the natural world. So for example, one of the first laws they discovered was the fact that, well, in the 4th century BC, Empedocles of Agrigentum said that light travels at finite speed. They didn't imagine, they had no idea what light was. I mean, the speed of light wasn't measured until the 18th century by a Danish astronomer, Ole Roma. But already 4th century before Christ, the Greeks said light travels at finite speed, and they also said that light takes the shortest path. So wherever light travels, it takes the shortest path. Okay. So as a consequence of that, they knew that if a ray of light hits a curved mirror, then the plane of incidence of the ray is equal to the plane of reflection of the ray, and the angle of incidence, that's the angle alpha there, is equal to the angle beta. Okay, so, but you see, they said, well, the law of reflection is really a consequence of a minima principle. And minima principles were known to the old Greeks. Now, one of the things you know about the modern world is that lots of people hire mathematicians. Wall Street hires mathematicians to try to figure out strategies to beat the next hedge fund in making, the billions of dollars. You have heard of all this, arbitrage, this fast trading on Wall Street. There are lots of mathematicians behind lots of these strategies. But the military's always hired mathematicians, because even the Duke of Milan hired Leonardo da Vinci, who wasn't really a mathematician, but he had hopes that he would help him, kill some of his neighbors in war. So this idea that mathematics is actually useful for the military, for the National Security Agency, that actually goes back to Greek times. Because now you can say to yourself, you're sitting in a class, and I've had all these students say, oh, why am I learning this? Is so what that the angle of incidence equals the angle of friction? Who gives a damn? What use is it? Nobody can use this. Well, remember, in the minds of geniuses, the insignificant, everything that's insignificant is significant, because they look more deeply behind all of these issues. And one such case was in 212 BC. There was this little island of Syracuse that had King Heron. And King made a terrible mistake, because there were two empires that were growing up in the Mediterranean. There was the Roman Empire, and there was the Carthaginian Empire. And they were economic rivals in the Mediterranean. Already in the 4th century BC, the Carthaginians destroyed Greek temples on the island of Sicily and so on. They hated each other. But the king of Sicily made a terrible mistake. He had, like Switzerland, had always been neutral. The Swiss figured it out, just declared neutrality. But somehow he decided to ally himself with Carthage against the Romans. Now, all of you may remember, you're still very young, but there was this movie called The Gladiator with Russell Crowe, which opens with this unbelievable military assault on the German armies in Germania. Finally, Marcus Aurelius, the great emperor, was going to create peace throughout the Roman Empire by defeating the Goths. And you see this horrific attack. And the assistant to Russell Crowe says, don't they know they're defeated? The onslaught of the Roman Empire was so brutal. And that's the value of some of these movies, because these people do a service by recreating some history. So, because Heron allied himself with Carthage, it triggered a Roman assault on the city. And there were Roman ships and so on. Now, it looked like it was doomsday for this little island and for the city of Syracuse. But Syracuse had its own secret weapon. The greatest genius of antiquity, the mathematician Archimedes. And Archimedes single-handedly built weapons using his ingenious ideas, using the principle of the lever that he discovered. And also this principle. Now, why was this principle interesting? So let's go to the next slide. Well, if you take an ellipse, now the ellipse had been studied by the people in the school of Plateau, and you can all say, why am I interested in an ellipse? You take a cone and you cut it with a plane, who gives a damn? Well, Archimedes knew that if you take, an ellipse is characterized by having two special points, called the foci. You take these two foci, P and Q, and let's suppose you're at Q and you shoot a light ray, and let's suppose this is a mirror, just use your imagination, and then it shoots off the mirror and hits Q. Now let's suppose the sun is at Q and you're at P. Well, that means all the intensity of the light, the sun's rays, would be focused on you and you'd be incinerated. Now, what can you do? Well, Archimedes knew another mathematical fact, that if you take Q and move it very, very far out to infinity, or very, very far, or out to infinity, whatever, it gets very, if you take it all the way to infinity, you get a parabola, but certainly if you take it very far out, you get a parabola. And a parabola then has this property that if you could build a parabolic mirror, you could focus the sun rays, and you could build a weapon using this idea. And in fact, rumor and legend has it that Archimedes built an array of these parabolic mirrors and incinerated the Roman fleet. This has gotten into the Roman historian, Roman history, and the legend books they call on burning mirrors. This battle was the first technological battle. It wasn't Star Wars. It was back in ancient Greece, using one simple fact of the reflection of light, because Archimedes was a genius who saw the significance in the insignificant. Now we'll get back. Here's a parabolic, here's a parabola, but I like this picture. Because, you know, if you throw a ball in the air, it travels on a parabolic path. That was discovered by Galileo in the 16th, early 17th century. So we'll get to that later again. Okay, here's a depiction, there are many in the literature, many depictions of this titanic battle between Syracuse and the Roman armies. Now the city did fall after 2 years of battle, but like Troy, it fell by trickery. It fell by having a traitor from the inside. Okay, so the Greeks looked at many shapes, not just polyhedral shapes. They looked at life, they looked at nature, and they wondered, why are things shaped the way they are? Why is the world the way it is? And of course, they looked for mathematical principles. So they looked at the hexagonal shape of a beehive, and they asked themselves, particularly mathematician Pappas, is it true that the bees actually build their hives, and that the hexagonal shape of the beehive is a consequence of the minimum principle? That is, the bees are being thrifty. The shape of the beehive, like the shape of the soap bubble, is a consequence of the fact that the bees are using the least amount of wax. Now, supposedly, in the 18th century, a Swiss mathematician by the name of Samuel Koenig supposedly proved this fact, which sent shockwaves throughout the scientific world at the time. Fontenelle, who was then the secretary of the French Academy of Sciences, explained and screamed, the bees have absolutely no intelligence, but they are using the highest possible mathematics by divine guidance and command. So the bees, are the bees really using the least wax? Well, here you see again hexagonal beehive. And there's a bee cell there. It looks like that. Actually, in this century, we found that there's a little cell that's slightly better than the actual bee cell. And this was discovered by a Hungarian scientist by the name of Phase Tuch, who wrote a book, a very famous book, What the Bees Know and What They Don't Know. So, but it's so marginal that the bees probably on a probabilistic basis, discovered something close to the opposite. Now, hexagonal shapes are common in nature. Now, you can go to Southern California, this is Devil's Postpile, you can see cracking in mud. And now, every time you see a similarity of pattern and a similarity of structure and form, the beehive is created by a living being. This is inanimate. This is a structure which is created by natural forces in the world. Why is this hexagonal shape? Could it be that, as the Greeks told us, that everything in the world can be explained by mathematical principles? Okay? So now here we go about the bubble. The bubble, I have some pictures. This is Jacques Rousseau, a painting from the 18th century. And here's Jean Chardin, a painting of a boy blowing a bubble. And my favorite, this is, you will not see this. This is only by luck that I have this picture because it's in the private collection of the Duke of Liechtenstein. And I was happened to be reading I was a professor in Germany for 3 years at the Ludwig University, and I had to be reading the Frankfurt Allgemeine, which is one of Germany's leading papers, and I found that the Duke had just bought this Rembrandt. And so we wrote to him and asked him if he could let us use this picture, which he did. Now it's in his castle, Schloss Ballhus. Okay, so now you can say, why aren't bubbles cubical? Why, every time you perform the experiment, it's always round? Like, why is the sun round? Is there a connection? Well, there's a man, there he is, Tom Noddy, he's much younger, of course we're all younger in those days. I met him once because he, in the 1970s, he thought he had created a cubical bubble. And somehow somebody told him it was impossible. You can't create a bubble. See, it's filled with smoke. See, that looks like a cube. It's a bad picture. I'm sorry. My resolution is not there. And so he came to see me, and he said, I think I created a cubical bubble. And I told him, unfortunately, not possible. Because something, a plane, as like when people thought the Earth was flat, if you go out in the ocean, if you take a sphere, a very large radius, it could look flat. So each of these sides of the so-called cube are actually spherical. Of course, you can always have fun with bubbles, and if you move them, they have different shapes. Now, we're talking about bubbles, which are not additive. What happens when you get to actually life, in the form and shape of life? Why are certain life forms shaped the way they are? How does evolution work? Well, we know we have Darwin's theory, but are there other components? So now, we all know about Darwin, but Darwin's expedition to the Galapagos was followed by another scientist expedition, Ernst Haeckel, who happened to be German, and he studied these unicellulas in the sea called Radiolaria. And you can see these skeletons here. And now I want you to look very carefully. I'm just here to be a little bit provocative. You can see the shape of the radiolarian skeleton. You can see there now a soap bubble in a tetrahedral frame. It looks exactly the same. So now we know, due to mathematical theory, that all the properties you see about soap films in frames or soap bubbles or configurations of soap bubbles all follow in this mathematical theorem. Therefore, it's absolute truth. That's what mathematics is. Otherwise, I'd be bored. I never liked art history or literature where everybody gives their opinion, and then there are these gray areas. It wasn't for me. I like right or wrong. I'm very limited. I like black or white. I don't like gray. Life is too tough. So, now here's another skeleton. And now here's the exact same shape and form created by a soap configuration. So you can build these yourself. And you can see here that this is explained by certain minimal principles. So then you can ask whether, in fact, minimal principles are actually involved in the creation of certain forms of life. In fact, Darcy Thompson, one of the most famous theoretical biologists that ever lived, wrote an incredible book called On Growth and Form, which is really more of a philosophical treatise. And he describes these attempts to understand nature through theoretical models. And now here you have, you can see spiral shapes, which looks like a double helix. And now, one of the things that allows soap films, as I said, to form is the reduction of surface tension. And there's also a whole theory of surface chemistry that goes on, and you can read books and books about it. This is a math lecture, so I'm not interested in the chemistry. The funny things and strange things happen when surfaces interact with air. There's a transition phase. There's a big difference between how a surface behaves, how a food behaves in its interior, and how it behaves at the surface where it's interacting with air. And of course, if you don't have soap, you have a much higher surface tension. And this surface tension allows the water beetle to glide along this, to actually walk on water. So there is a creature that walks on water. And one of my favorite poems is from the poet Hilaire Belloc about the water. And he goes as follows. The water beetle here shall teach a sermon far beyond your reach. He glides across the water's face with ease, celerity, and grace. But if he ever stopped to think of how he actually did it, he would sink. Okay, now, more about soap. I could take my little gun and I could sit there on the floor and shoot bubbles and make configurations of bubbles and bubbles like beer foam, right? Again, it's bad resolution. It's really, I couldn't get a better picture off the internet. Okay, so there's a configuration of soap bubbles. You can use your imagination. Now, take two glass plates, crush it between these soap bubbles between two glass plates. And there you see it. Now you can put a wire in there for good measure. So here's a soap film configuration just crushed between two glass plates. And now, amazingly, you see this hexagonal form. Here, all these hexagons. But when the soap film actually hits the wire, you get angles of 90 degrees. Always 90 degrees. Here you have 120 degrees. The classic hexagonal shape. Now, why is the soap doing this? Because it's following a principle of economy of heat. Maximum, minimum. And there it is. Always. And you can prove that it has to be this way. It's a mathematical theorem. Once you just assume that the configuration has to satisfy a minimum property, this is the result. Now, of course, you can say, this is uninteresting. I don't care about this. It's boring. Now, wonder how God created the world, who created the world. Now we take one picture and compare it to the wings of a dragonfly. Not to go too deeply into these questions. But remember, we're trying to understand the scientific principles at the root of the creation of the universe and the creation of life itself. And now, by simple examples, to lead us on, you see that the wings of a dragonfly, which is the structure of a living being, this picture looks exactly like that picture. You have the same 90 degrees, the same 120 degrees in a living being as you do if you just make some, inanimate soap. Okay, now you can wonder about a standard problem. You have to connect, let's say, 4 cities, and you have to do it build a system of roads that is the least expensive. So you have to have the shortest set of roads, the shortest connections between sets of points. This problem in the mathematical literature goes back to the 19th century. It's called Steiner's problem. And of course, mathematics is difficult and so on. But you know, when you ask nature, if you ask a mathematician to solve some simple problem, tell me how to build the shortest system of road, you think, you worry. Just like if I ask or try to ask a mathematician, what is the surface of least area forming this contour, spanning this contour? It's, well, almost impossible. But nature has no problem. It does it instantly. It doesn't even think. So, there, put this into soap. In other words, take these pins and make little rods, dip it into a soap solution, and then you're going to get a solution to the problem. You don't even need any advanced mathematics. Nature is doing it on its own. Now, the person who made this field of soap films and minimal surfaces popular was a Belgian physicist by the name of Plateau. He was a rather eccentric fellow, and he was not a mathematician, but he was fascinated with the multitude and variety of surfaces you could produce by this experiment, by dipping soap into solution. And he asked many, many mathematicians about the problem, about how you could actually prove. I mean, it's not clear that if you take an arbitrarily closed contour, that there is a surface of least area spanning that contour. How do you know that? Well, if you study calculus, you study how to find maximum, minimum differentiable functions on a closed interval. Well, this is a problem way beyond that. This is really a deep, deep problem. He was so obsessed with talking to mathematicians and finding a solution that on his honeymoon in Paris, he left his wife at the hotel and started to go to the university there, the University of Paris, and met some mathematicians, and became so involved in the discussions, he disappeared for 3 days. So it's amazing that his wife actually still stayed with him. So the person who actually gave the mathematical formulation of the problem was the great German genius Carl Weierstrass. The whole theory of calculus, remember, was really founded by this man. He was a high school teacher for a good part of his life, and only discovered by the German mathematical establishment in his 40s. He spent 20 years as a high school teacher, but became one of the greatest mathematicians of the 19th century. But he's the one that formulated the problem mathematically. And because of Plateau had done all the experiments and brought great attention to this problem, the solution to this problem became known as Plateau's problem. Now the word Plateau's problem is used to cover an enormous number of mathematical problems, but this became the greatest unsolved problem of the 19th century. I mean, again, nature finds it trivial to find a solution of a surface of least area spanning a contour, but now you have the mathematical problem. Well, it remained unsolved. Many famous mathematicians, Lebesgue, Darboux, worked on this problem and could find no solution. Now remember, in the early 20th century, there were very few American mathematicians that were recognized as being worked on. I mean, all of mathematical work and theory was centered in Europe, in particular in Paris and in Germany, in the city of Göttingen in eastern Germany. And so it was surprising in that in 1928, this gentleman, Jesse Douglas, an American, gave a lecture in Göttingen in which he actually announced a solution to this problem, that there exists a mathematical proof that given any contour, there is a surface of least area. So for this, he got the first Fields Medal in mathematics, first Nobel Prize, you could say. Now, there was no Nobel Prize in economics that was bequeathed by the Swedish industrialist Alfred Nobel. In fact, this Nobel Prize in economics was funded by the Swedish banks in the later part of the 20th century, mid-20th century. But they could still call it a Nobel Prize. However, the will of Alfred Nobel specifically ruled out the possibility that any mathematician at any time, no matter who ever put up the money, would ever be able to get a Nobel Prize. And the reasons for this are, well, it's not worth getting into them right now. Anyway, here's another system of soap films. And here, by the way, you see the characteristic property of soap films. You see you have either 4 lines coming together at 190 degrees or 3 surfaces coming together at 120 degrees. All of this can be proved using, the fact that it's a surface of minimal area. Now here, you can take 2 wands. I have wands here. See these little wands? Oh my God, again. You could try to do it. I'm sure I won't be able to do it. I've got copper. But you could try to form, no, I better not waste any time on it. But if you take these 2 wires, 2 circular wires or 2 wands, you can get surfaces of different topological types. Like, this is not a disk here. This is what's called, this is a catenoid. And it's a basic topological type of what we call an annulus. Now the soap is not. It is an annulus, it's a washer, and I can pull this up, and there you get an annular type soap. Now, given any kind of topological type, there's a sphere is one typological type. Here's a donut. And so now what I can do is I can take the donut and cut a hole out of it, and that creates the wire here, just like the boundary of the disk. There's this little circle here. I can cut out a disk here, and that creates a new type of shape. And here you can see you have soap film actually takes this other type of a donut shape here. Here's a disk minimal surface. Here's another disk minimal surface. So you have the same contour here, and you can actually get 3 types of soap film surfaces. Now, there was no theorem in the mathematical literature that says that if you have a curve of this type, there is exactly a soap film surface of this shape. So, I mean, I and a co-author in Germany at Heidelberg University, who were the first to prove that this actually surface exists mathematically. Not, I mean, nature always finds it, but to provide a mathematical proof that if a wire looks like this, a contour looks like this, then there actually is this more complicated topological shape, so forth. Okay. Now, you can ask, okay, why should even somebody spend their time working mathematically on a problem like soap films? Well, because soap films are really a very, very deep and profound mathematical theory about maxima and minima. The same things you study in calculus, 1, but those are really relatively trivial problems. This is highly non-trivial. Now, the Greeks said that nature follows laws, and that these laws are mathematical laws. About the 16th century, people began to think that, they all believed, by the way, that God created the universe, that there was a creation. The Greeks even said, even in the Platonic school, the universe began when time began. There was a beginning, even though they had never heard of the Big Bang, the creation of the universe. There was a creation. And most people throughout the centuries believed that God created the universe. But at the time that God created the universe, that God set in motion mathematical laws that would govern everything in the universe. Its creation, its expansion, all forms, all laws, all phenomena, electricity, magnetism, gravity. There were all of these laws, and in the 16th century they began to wonder, is there one law that at the very moment of creation, when God, or however it happened, at the very instant of creation, one law that God set in motion from which everything follows. One simple mathematical law. Not a whole plethora of laws. And so what we have to do is we have to look around nature and ask, well, if there is such a law, what would it look like? Well, already people knew about the beehives. People knew about the fact that light takes the shortest path. The 17th century French mathematician Fermat, who founded coordinate geometry, said that light takes the least time. That's called Fermat's principle in optics. So there was always these least principles. A straight line is the shortest distance between 2 points. Now, one of the problems that the ancient Greeks had wondered about is why the planets move the way they do. You see, if you think that the Earth is the center of the universe, you see, then you have a problem, because if you look at Mars, Mars goes forward, then goes backwards. Now, this is bizarre. Why would a planet go forward and then backward? Of course, the problem is that the Earth is not the center of the universe. But, you know, so they had to try to explain this retrograde motion. But the Greeks never succeeded. They came up with a theory called the Ptolemaic theory. They never succeeded in understanding how the planets move in time as they revolve around the sun. That had to wait till Isaac Newton in the latter part of the 17th century, who had this theory of forces. So he hypothesized, for those of you who take elementary physics, that if you take a look at the Earth and you take a look at the sun, there's a force of attraction acting over the 92 million miles, holding the Earth in orbit around the sun. Now, this is, everybody was astounded because Newton was able to derive the fact that the planets move in elliptical orbits as had been predicted, or been shown by Kepler. But Newton himself was very disturbed by this. Now, remember, when you have a genius like Archimedes, like Isaac Newton, and he's trying to talk to normal people like us, maybe, I don't want to insult anybody in the audience, but I'm certainly normal. And when he's talking to us, it's often misunderstood. When they take a great man like Isaac Newton, we tend to deify the person and not actually quite listen to what this individual is saying to us. So it turns out that not only did Leibniz and others have a great doubt about Newton's theory, but Newton himself, he writes in a letter, you see, this idea that there is this force holding the Earth to the sun sounds even to Newton absurd. But nevertheless, it's still taught in physics. Everybody learns it. But Newton himself writes to his friend, Richard Bentham, that gravity, which is the force between the Earth and the sun, should be innate, inherent, and essential to matter, so that one body, like the sun, may act upon another, at a distance through which their action may be conveyed from one to the other. To me, Isaac Newton is so great an absurdity that I believe that no man who in philosophical matters has a competent faculty of thinking could ever fall into it. You have to be an imbecile. It worked. It worked. It predicted something. But you see, the Greeks taught us that our job in life, if you want to understand the creation, is to, and by the way, this is the point of view, not myself, but if you look at the greatest scientists and the greatest scholars, they wanted to understand the mind of God. And that's exactly how Albert Einstein put it. Our goal is to understand the mind of God. His challenge to us is to understand the laws that were laid down, the mathematical laws that were laid down at the time of creation. Now, 20th century, they began to see that Newton's theory didn't work. It couldn't explain the orbit of Mercury. It has certain abnormalities that could not be explained. And so this was the great challenge. How can you explain gravity without using the idea of a force? And now, the whole idea was due to Albert Einstein. So let me just give you, and I'll make a point, let me give you a little lecture here, a little discussion here. You have a trampoline, and it's very taut, and so just like surface tension, if I roll a ball across the trampoline, it'll roll in a straight line. Now let's suppose, in the next slide, suppose I put some huge heavy ball in the middle of the trampoline. It's going to curve the trampoline. And now, when I try to roll a ball across the surface of the trampoline, it will travel in a curved path. So Einstein's theory was the following. Matter and the universe is curved. It's like a trampoline. It's only a four-dimensional, curved surface. And that matter and energy curve that surface. And that light, always in this curved universe, curved by matter and curved by energy, always takes the shortest path. The trajectories that we see in a curved universe are all shortest paths. Just like the light, just like the soap film is the least. It's always a minimum principle at work. In fact, in 1707, well, here's Einstein, and before we get ahead of ourselves, Einstein's theory was an astounding accomplishment because he showed that light is bent by matter, that light ray traveling near the sun is curved, that the universe, Einstein's theory again predicted the universe had a beginning, and the universe is expanding. Now, the person who actually had the vision to write down the first universal law of mathematical law to describe all phenomena in nature, not just soap films, not just soap bubbles, but everything, was Leibniz, Gottfried Wilhelm Leibniz, who in 1707 wrote a letter expounding on what he called the principle of least action. This principle of least action says that nature always minimizes the expenditure of energy over time, just like the soap film minimizes area, or the soap bubble minimizes area containing a volume. Every physical phenomenon in nature, according to Leibniz, is based on this principle. And this principle was an outgrowth of his philosophical treatise called the Theodicee, which it's just an unbelievable treatise. And those of you who ever studied Voltaire's Candide, which was a book written to criticize and to attack Leibniz and Newton, this theory had profound consequences in the future. Okay, but it was based on this Theodicee, which says that the philosophical treatise said this world is not a perfect world. You see, Leibniz was confronted as a deeply religious man and a believer in the creation of the universe by God. Leibniz was troubled by the fact that sin and evil exist. Wherever we look, there are people being slaughtered all around the world. There's the Holocaust. There's all kinds of terrible tragedies that have occurred across the world. Sin and evil do exist, but Leibniz was trying to explain sin and evil by a philosophical principle that all you can do is the best of all possible worlds. That God does not have the power to create a perfect world, because sin and evil are necessary. The outgrowth of that philosophical attempt to explain the world that we live in led to the principle of least action. Now, the principle of least action explains Maxwell's equations, which allow electricity and magnetism, which allow you to make cell phone calls. For example, have you ever asked yourself, I have a few more minutes, I'll end. How can you discover radio waves, cellular waves? How can you discover them? Nobody can see them. You can't smell them. You can't hear them. How did this happen? How can mankind discover something that is invisible to every possible sense? Well, it was discovered because it was predicted mathematically. Mathematicians discovered this and predicted the existence of radio waves. It's again another indication of the power of mathematical thought to penetrate and to understand the natural world. Now, for example, I have a quote I saw outside in the hallway when I went up to the restroom. There's a picture of Richard Feynman. He's one of my great heroes, and I often quote him in my vector calculus book. Feynman always asked the question, how do we get from here to there? So, for example, just as Galileo observed, let me go ahead here, there's Feynman, my hero, playing the drums. There's a parabola, you shoot a hose out, it's a parabola. You could get into the whole theory of forces, and so on and so forth, and study freshman physics, and write down the equation, and all that. Let me quote Feynman. Feynman was one of the greatest professors ever to live, because unlike most university professors that just put the theorems and the formulas on the board, he always tried to explain to his students the deeper reasoning, the deeper ideas. So he talked about a high school teacher he had. This is quoting Feynman, who won the Nobel Prize for the creation of quantum electrodynamics. When I was in high school, my physics teacher, whose name was Mr. Bader, called me down one day after physics class and said, "Feynman, you look bored." Because Feynman was very smart, bored by everything. "I want to tell you something interesting." Then he told me something which I found absolutely fascinating, and have since then always found fascinating. Every time the subject comes up, I work on it. In fact, when I began to prepare this lecture, I found myself making more analyses on the thing. And instead of worrying about my lecture, which a lot of professors don't worry about, I got involved in a new problem. And in fact, he even goes on to say that he owes his Nobel Prize to his high school teacher for providing him with a significant insight. Why? When you throw the ball up, as Galileo observed, is it a parabola? In other words, as Feynman says, how do you get from here to there? There are theoretically lots of paths. Why the parabola? Well, you could use Newton's law of gravitation. But Mr. Beatty told Feynman, no, you don't need force. You don't need gravity. Get rid of it. All you need is a maximum and minimum principle. That the parabola is a unique path that minimizes an energy in the exact sense of Leibniz. That if you take from time 1 to time 2, and you take the kinetic energy of the particle minus potential energy, so this is, let's say, dy dt squared. That's the velocity, potential energy. It's an integral. So y of t is a function. Here's y, here's t. That if you take this among all possible functions, and you ask, is there a minimum? It's a unique minimum. One and only one, it's the parabola. So it's not gravity, it's not force, it's a minimum principle. And it set Feynman on a whole lifetime of thinking of Leibniz's principle of least action. Now, I want to end my lecture, my little talk here, because I think it is really important. Wow. Sorry. I want my little mouse. Okay, I wanted to, I'm somehow it's frozen. Okay, so let me just go back here. I want to end. One of the great believers in the principle of least action was the greatest German physicist, except for Einstein, in the 20th century, Max Planck, who actually was the creator, along with Einstein, of the quantum universe, that nature's quantized. I'm going to read two excerpts of a lecture that Planck gave. One in 1922 after the First World War. And it's on Leibniz Day. So the Germans celebrate Leibniz Day. And he's talking about Leibniz and his philosophy. Now, Planck was a deist. He was a very religious man. Like many great scientists, was a very religious man. And he was very disturbed by the fact that this principle, the principle of least action, which is behind Einstein's theory of relativity, which is behind Maxwell's equations of electromagnetism, which is even behind Newton's theory of gravitation. All of these great theories of science are all, in fact, a consequence of the principle of least action. This is Max Planck, and I'll close with this. He's referring to Leibniz on Leibniz Day, which was June 29, 1922. The theodicy culminates with the statement that whatever occurs in our world, in the large as well as in the small, in nature as well as in spiritual life, is once and for all regulated by divine reason, and in such a way that our world is the best among all possible worlds, which was Leibniz's philosophy. Would Leibniz reaffirm this statement today in the event of the misery of the present time, in view of the bitter failure of many efforts not immediately aimed at material gain, in view of the undeniable fact that the imagined general harmony of people today seem to be further away from its realization than ever? No doubt, we would have to answer this question in the affirmative, even if we did not know that Leibniz never ceased to earnestly occupy himself until the very last years of his life, amid many disappointments of all kinds. And we shall hardly err in assuming that it was exactly his philosophy in the theodicy that gave him support and comfort in the most sorrowful days of his life. This, once again, is a touching example of the old truth that our most profound and most sacred principles are firmly rooted in our innermost and souls, independent of experience. Modern science, in particular, under the influence of the development of the notion of causality, has moved away from Leibniz's teleological point of view. Modern science has abandoned the assumption of a special, anticipating reason, and considers each event in the natural and spiritual world, at least in principle, reducible to prior states. Present-day physics, as far as theoretically organized, is completely governed by a system of space-time differential equations. This entire rich system of differential equations in all of modern theoretical physics is contained in a single principle, in a single theorem of Leibniz, the principle of least action. In present-day physics, the principle of least action plays a relatively minor role. It does not quite fit into the framework of present theories. Of course, it is a correct statement, but it usually does not serve as the foundations of a theory. Then, in 1935, again on Leibniz Day, he had the following short remarks to make in honor of the great man Leibniz. Today, when it appears the world is now on the verge of another catastrophic and horrific war, as if the First World War was not enough. Today, when it appears to be more and more difficult to find a reasonable sense in the development of humanity, this sentence, that this is the best of all possible worlds, this sentence may seem grotesque by its audacity. Would Leibniz maintain this in the face of the present events, the terrors of the World War, the general mutual distrust and ever-increasing armaments of peoples? We would have to affirm this question even if we would not know that Leibniz neither lost his philosophy by the hard ravages of the 30 Years' War, reaching into the first years of his life, nor by the subsequent deep humiliation of his country. Namely, it is a matter of fact that the philosophy of the Theodicee can neither be proved nor disproved. It is not the result of experience, but the supposition and starting point of Leibniz's outlook on the universe. According to his philosophical point of view, any apparent contradiction, each suffering, every separate injustice in the world can be traced to the fact that our limited human understanding is unable to recognize the whole connection of any single event with the entire plan of the creation. Thus, it is even more surprising that Leibniz's principle of least action has been found to be valid without restriction throughout the entire physics of our time. Recently, David Hilbert has shown that Einstein's general theory of relativity follows from the principle of least action. The more complicated circumstances become, the less likely it is that the dominance of such a simple law as in the creation of the sofa the more complicated the circumstances become, the less likely it is that the dominance of such a simple law could be a mere accident. Postscript. Planck's oldest son, Carl, was killed in Verdun in 1916. Both daughters died when giving birth to their first child. The youngest son, Erwin, because he had been involved in the von Stauffenberg assassination attempt on Hitler's life, was executed in 1944. Shortly thereafter, at the end of the war, Planck lost all his personal belongings, and at almost 87 years of age, he found himself in the great trek of refugees to the west, just like millions before and after him. Thank you very much.
Matthew would like to present Mr. Tromba with a bit of appreciation.
Thank you very much. That's very nice of you. Oh, thank you. Oh, and a book too.
Yes, Professor Palmer.
Oh, great. Thank you. Thank you very much. Well, as I said, I have 1,500 to 2,000 pages of mathematics in case you're interested.
So thanks so much for coming, everyone. Feel free to step out if you need to go to class or anything. And if you'd like to stick around and ask a couple of questions, you're welcome to do it. Thanks so much.
Was that your popular book you were reading from?
Yeah.
Okay.